Chapter 13. Art of heating, ventilating, cooking, refrigeration and lighting. That Prometheus stole fire from heaven to give it to man is perhaps as authentic an account of the invention of fire as has been given. It is also reported that he brought it to earth in a hollow tube. If a small stick or twig had then been dipped into the divine fire, the suggestion of the modern match may be supposed to have been made. But men went on to reproduce the fire in the old way by rubbing pieces of wood together, or using the flint, the steel and the tinder until 1680, when Godfrey Hankwitz of London, learning of the recent discovery of phosphorus and its nature, and inspired by the Promethean idea, wrapped the phosphorus in folds of brown paper, rubbed it until it took fire, and then ignited there at one end of a stick which he had dipped in sulfur, and this is commonly known as the first invented match. There followed the production of a somewhat different form of match, sticks first dipped in sulfur, and then in a composition of chlorate potash, sulfur, colophony, gum of sugar, and cinnabar for coloring. These were arranged in boxes, and were accompanied by a vial containing sulfuric acid, into which the match was dipped, and thereby instantly ignited. These were called chemical matches and were sold at first for the high price of 15 shillings a box. They were too costly for common use, and so our fathers went on to the 19th century using the flint, the steel and the tinder, and depending on the coal kept alive upon their own or their neighbor's hearth. Prometheus, however, did reappear about 1820-25, when a match bearing the name Promethean was invented. It consisted of a roll of paper treated with sugar and chlorate of potash, and a small cell containing sulfuric acid. This cell was broken by a pair of pliers, and the acid ignited the composition by contact therewith. It was not until 1827-29 that John Walker, chemist at Stockton-upon-Tees, improved upon the idea of Prometheus and Hankwitz of giving fire to men in a hollow tube. He used folded sanded paper. It may have been a tube, and through this he drew a stick coated with chlorate of potash and phosphorus. This successful match was named Lucifer, whose other name was Phosphor, the morning star, and the king of the western land. Faraday, to whom also was given Promethean inspiration, procured some of Walker's matches, and brought them to public notice. In many respects the mode of their manufacture has been improved, but in principle of composition and ignition, they remain the same as Walker's today. In 1845, Schroeder of Vienna discovered amorphous or allotropic phosphorus, which rendered the manufacture of matches less dangerous to health and property. Tons of chemicals and hundreds of pine trees are used yearly in the making of matches, and many hundreds of millions of them are daily consumed. But this vast number of matches could not be supplied had it not been for the invention of machines for making and packing them. Thus in 1842 Reuben Partridge of America patented a machine for making splints. Others for making splints and the matches separately, quickly followed. Together with these came match dipping and match box machines. The splint machines were for slitting a block of wood of the proper height downward nearly the whole way into match splints, leaving their butts in the solid wood. These were square and known as block matches. Other mechanisms cut and divided the block into strips, which were then dipped at one end, dried and tied in bundles. By other means, a swing blade, for instance, the matches were all severed from the block. Matches are made round by one machine by pressing the block against a plate having circular perforations, and the interspaces are beveled so as to form cutting edges. Poirier, a Frenchman, invented a machine for making match boxes of pasteboard. Suitable size rectangular pieces of pasteboard rounded at the angles for making the body of the box are first cut, then these pieces are introduced into the machine, where by the single blow of a plunger, they are forced into a matrix or die and pressed, and receive by the single motion their complete and final shape. The lid is made in the same way. By one modern invention, matches after they are cut are fed into a machine at the rate of 100,000 an hour, onto a horizontal table, each match separated from the other by a thin partition. They are thus laid in rows, one row over another, and while being laid, the matches are pushed out a little way beyond the edge of the table, a distance far enough to expose their ends, and to permit them to be dipped. When a number of these rows are completed, they are clamped together in a bundle and then dipped first into a vessel of hot sulfur, and then into one of phosphorus, or other equivalent ingredients may be used or added. After the dipping they are subjected to a drying process and then boxed. Processes differ, but all are performed by machinery. In many factories where phosphorus is used without great care, workmen have been greatly affected thereby. The fumes of the phosphorus attack the teeth, especially when decayed, and penetrate to the jaw, causing its gradual destruction, but this has been avoided by proper precautions. The greatly increased facility of kindling a fire by matches gave an impetus to the invention of cooking and heating stoves. Of course, stoves, generically speaking, are not a production of the 19th century. The Romans had their Laconic Amer heating stove, which from its name was an invention from Laconia. It probably was made in most cases of brick or marble, but might have been of beaten iron, was cylindrical in shape, with an open cupola at the top, and was heated by the flames of the hypocaust beneath. The hypocaust was a hot air furnace built in the basement or cellar of the house, and from which the heat was conducted by flues to the bathrooms and other apartments. The Chinese ages ago heated their hollow tile floors by underground furnace fires. We know of the Athener of the alchemists of the Middle Ages. Knight calls it the original base-burning furnace. A furnace of iron or earthenware was provided on one side with an open stack or tower which opened at the bottom into the furnace, and which stack was kept filled with charcoal or other fuel, which fed itself automatically into the furnace as the fuel on the bed thereof burned away. Watt introduced an arrangement on the same principle in his steam boiler furnace in 1767, and thousands of stoves are now constructed within England and the United States, also embodying the same principle. The earthenware and soapstone stoves of continental Europe were used long before the present century. In Ben Franklin's time in the American colonies, there was not much of a demand for stoves outside of the largest cities, where wood was getting a little scarce and high, but the philosopher not only deemed it proper to invent an improvement in chimneys to prevent their smoking, and to better heat the room, but also devised an improved form of stove, and both inventions have been in constant use unto this day. Franklin invented and introduced his celebrated stove, which he called the Pennsylvania Fireplace, in 1745, having all the advantages of a cheerful open fireplace and a heat producer, and which consisted of an iron stove with an open front set well into the room, in which front part the fire was kindled, and the products of combustion conducted up a flue, and thence under a false back and up the chimney. Open heat spaces were left between the two flues. Air inlets and ampers were provided. In his description of this stove at that time, Franklin also referred to the iron box stoves used by the Dutch, the iron plates extending from the hearths and sides, etc., chimneys making a double fireplace used by the French, and the German stove of iron plates, and so made that the fuel had to be put into it from another room, or from the outside of the house. He dwells upon the pleasure of an open fire, and the destruction of this pleasure by the use of the closed stoves. He also describes the discomforts of the fireplace in cold weather, the cold draught nipping one's back and heels scorched before, and frozen behind the sharp draughts of cold from crevices from which many catch cold, and from whence proceed coughs, catarrhs, toothaches, fevers, pleurisy, and many other diseases. Added to the pleasure of seeing the crackling flames, feeling the genial warmth, and the diffusion of a spirit of sociability and hospitality, is the fact of increased purity of the air by reason of the fireplace as a first-class ventilator. Hence it will never be discarded by those who can afford its use, but it alone is inadequate for heating and cooking purposes. It is modernly used as a luxury by those who are able to combine with it other means for heating. The great question for solution in this art at all times has been how to produce through dwelling houses and larger buildings in cold and damp weather a uniform distribution and circulation of pure heated air. The solution of this question has of course been greatly helped in modern times by a better knowledge of the nature of air and other gases, and the laws which govern their motions and combinations at different temperatures. The most successful form of heating coal stove of the century has been one that combined in itself the features of base burning. That is, a covered magazine at the center or back of the stove, open at or near the top of the stove into which the coal is placed, and which then feeds to the bottom of the fire pot, as fast as the coal is consumed, a heavy open fire pot placed as low as possible, an ash grate connected with the bottom of the pot, which can be shaken and dumped to an ash box beneath without opening the stove, thus preventing the escape of the dust, an illuminating chamber nearly or entirely surrounding the fire pot, provided with mica windows, through which the fire is reflected, and the heat radiated, a chamber above the fire pot, and surrounding the fuel chamber, and into which the heat and hot gases arise, producing additional radiating surface, and permitting the gases to escape through a flue in the chimney, or leading them first through another chamber to the base of the stove and thence out, and amperes to control and regulate the supply of air to the fuel, and to cut off the escape or control the course of the products of combustion. The cheerful stove fireplace and stove of Franklin and the French were revived, combined and improved some years ago by Captain Douglas Galton of the English Army for use in barracks, but the stove is also admirably adapted for houses. It consists of an open stove or grate set inner at the front of the fireplace, with an air inlet from without, the throat of the fireplace closed, and a pipe extending through it from the stove into the chimney. Although a steady flow of heat, desirable regulation of temperature and great economy in the consumption of fuel, by reason of the utilization of so much of the heat produced, were obtained by the modern stove, yet the necessity of having a stove in nearly every room, the ill ventilation due to the non-supply of pure outer air to the room, the occasional diffusion of ash dust and noxious gases from the stove, and inability to heat the air along the floor, gave rise to a revival of the hot air furnace, placed under the floor in the basement or cellar, and many modern and radical improvements therein. The heat obtained from stoves is affected by radiation, the throwing outward of the waves of heat from its source, while the heat obtained from a hot air furnace is affected by convection, the moving of a body of air, to be heated to the source of heat, and then when heated bodily conveyed to the room to be warmed. Hence in stoves and fireplaces, only such obstruction is placed between the fire and the room, as will serve to convey away the obnoxious smoke and gases, and the greatest facility is offered for radiation, while in hot air furnaces, although provision is also made to carry away the smoke and impure gases, yet the radiation is confined as closely as possible to chambers around the fire space, which chambers are protected by impervious linings from the outer air, and into which fresh outdoor air is introduced, then heated and conveyed to different apartments by suitable pipes or flues, and admitted or excluded, as desired, by registers operated by hand levers. There are stationary furnaces and portable furnaces. The former class enclose the heating apparatus in walls of brick or other masonry, while in the latter the outer casing and the inner parts are metal structures, separable and removable. In both classes an outer current of pure air is made to course around the fire chamber, and around among other flues and chambers through which the products of combustion are carried, so that all heat possible is utilized. Vessels of water are supplied at the most convenient place in one of the hot air chambers to moisten and temper the air, and amperes are placed in the pipes to regulate and guide the supply of heat to the rooms above. After Watt had invented his improvements on the steam engine, the idea occurred to him of using steam for heating purposes. Accordingly, in 1784, he made a hollow sheet iron box of plates, and supplied it with steam from the boiler of the establishment. It had an air escape cock and condensed water escape pipe. And in 1799 Boulton and Watt constructed a heating apparatus in Lee's factory, Manchester, in which the steam was conducted through cast iron pipes, which also served as supports to the floor. Patents were also taken out by others in England for steam heating apparatuses during the latter part of the 18th century. Heating by the circulation of hot water through pipes was also originated or revived during the 18th century, and a short time before Watt's circulation of steam. It is said that Bonamain of England, in 1777, desiring to improve the ancient methods of hatching poultry by artificial heat practiced by both ancient and modern Egyptians, ages before it became a latter-day wonder, and taught the Egyptians by the ostriches, conceived the idea of constructing quite a large incubator building with shelves for the eggs, coops for holding the chickens, and a tube for circulating hot water leading from a boiler below and above each shelf, and through the coops, and back to the boiler. This incubator contains the germs of modern water heaters. In both the steam and water heating systems, the band or collection of pipes in each room may be covered with ornamental radiating plates, or otherwise treated or arranged to render them sightly and effective. In one form of the hot water system, however, the collection of a mass of pipes in the rooms is dispensed with, and the pipes are massed in an air chamber over or adjacent to the furnace, where they are employed to heat a current of air introduced from the outside, and which heated pure air is conveyed through the house by flues and registers as in the hot air furnace system. The hanging of the grain, the turning of the spit, the roasting in ashes and on hot stones, the heating of and the baking in the big Dutch ovens, and some other forms of cooking by our forefathers, have their pleasures and advantages, and still are appreciated under certain circumstances, and for certain purposes, but are chiefly honored in memory alone and reverenced by disuse, while the modern cooking stove with its roasting and hot water chambers, its numerous seats over the fire for pots, pans, and kettles, its easy means of controlling and directing the heat, its rotating grate, and, when desired, its rotating fire chamber, for turning the hot fire on top to the bottom, and the coal-choked fire to the top, its cleanliness and thorough heat, its economy in the use of fuel, is adopted everywhere, and all the glowing names with which its makers and users christen it, fail to exaggerate its qualities when rightly made and used. It would appear that the field of labor and the number of laborers, chiefly those who toiled with brick and mortar, were greatly reduced when those huge fireplaces were so widely discarded. This must have seemed so especially in those regions where the houses were built up to meet the yearning wants of an outside chimney, but armies of men are engaged in civilized countries in making stoves and furnaces, where 3/4 of a century ago very few were so employed. As in every industrial art, old things pass away, but the new things come in greater numbers, demand a greater number of workers, develop new wants, new fields of labor, and the new and increasing supply of consumers refuse to be satisfied with old contrivances. In the United States alone there are between 400 and 500 stove and furnace foundries, in which about 10,000 people are employed, and more than 3 million stoves and furnaces produced annually, which require nearly 1 million tons of iron to make, and the value of which is estimated as at least $100 million. The matter of ventilation is such a material part of heating that it cannot escape attention. There can be no successful heating without a circulation of air currents, and fortunately for man and his house, no good fire can be had without an outflow of heat, and an inflow of cooler air. The more the circulation is prevented, the worse the fire and the ventilation. In the United States alone there are between 400 and 500 stove and furnace foundries, in which about 10,000 people are employed, and more than 3 million stoves and furnaces produced annually, which require nearly 1 million tons of iron to make, and the value of which is estimated as at least $100 million. The matter of ventilation is such a material part of heating that it cannot escape attention. There can be no successful heating without a circulation of air currents, and fortunately for man and his house, no good fire can be had without an outflow of heat, and an inflow of cooler air. The more the circulation is prevented, the worse the fire and the ventilation. It seems to many such a simple thing, this change of air only to keep open the window a little to have a fireplace, and convenient door. And yet some of the brightest intellects of the century have been engaged in devising means to accomplish the result, and all are not yet agreed as to which is the best way. How to remove the heated, vitiated air and to supply fresh air while maintaining the same uniform temperature is a problem of long standing. The history of the attempts to heat and ventilate the Houses of Parliament since Wren undertook it in 1660 has justly been said to be history of the art of ventilation. Since that time, as the most eminent scientific authorities in the world have been engaged or consulted in it, and the most exhaustive reports on the subject have been rendered by such men as Gay-Lussac, Sir Humphrey Davy, Faraday, and Dr. Arnott of England and Gen. Morin of France. The same may be said in regard to the Houses of Congress in the United States Capitol for the past 35 years. Prof. Henry, Dr. Billings, the architect, Clark, of that country, and many other bright inventors and men of ability, have given the subject devoted attention. Among the means for creating ventilation are underground tunnels leading to the outer air, with fans in them to force the fresh air in or draw the poor air out, holes in the ceiling, fireplaces, openings over the doors, openings under the eaves, openings in the window frames, shafts from the floor or basement, with fires or gas jets to create an upward draft, floors with screened openings to the outer air, steam engines to work a suction pipe in one place, and a blowpipe in another, air boxes communicating with the outer air, screens, hoods, and deflectors at these various openings. All these, separately or in combination, have been used for the purpose of drawing the vitiated air out, and letting the pure air in without creating drafts to chill the sensitive, or overheating to excite the nervous. There seems to have been as many devices invented to keep a house or building closed up tight while highly heating it, as to ventilate the same and preserve an even moderate temperature. The most approved system of ventilation recognizes the fact that air is of the same weight and is possessed of the same constituents in one part of a room as in another, and to create a perfect ventilation, a complete change in circulation must take place. It therefore creates a draft, arising from the production of a vacuum by a current of heat or by mechanical means, or by some other way, which draws out of a room the used up, vitiated air through outlets at different places, while pure outer air is admitted naturally, or forced in if need be, through numerous small inlets, such outlets and inlets, so located and distributed and protected as not to give rise to sensible drafts on the occupants. The best system also recognizes the fact that all parts of a house, its cellars and attic, its parlors and kitchens, its closets, bathrooms and chambers, should be alike clean and well ventilated, and that if one room is infected all are infected. The laurels bestowed on inventors are no more worthily bestowed than on those who have invented devices which give to our homes, offices, churches and places of amusement a pure and comfortable atmosphere. Car heaters. The passing away of the good old portable foot stove for warming the feet, especially when away from home, and while traveling, is not to be regretted, although in some instances it was not at first succeeded by superior devices. For a long time after the introduction of steam, railroad cars and carriages, in which any heat at all was used, were heated by a stove in each car generally kept full of red-hot coal, or wood, an exceedingly dangerous companion in case of accident. Since 1871 systems have been invented and introduced, the most successful of which consists of utilizing the heat of the steam from the locomotive, for producing a hot water circulation through pipes along the floor of each car, and in providing an emergency heater in each car, for heating the water, when steam from the locomotive is not available. Waste hay and straw, and similar combustible refuse, are found in great abundance. Stoves have been invented especially designed for the economical consumption of such fuel. One requisite is that such light material should be held in a compressed state while in the stove to prevent a too rapid combustion. Means for so holding the material under compression appear to have been first invented and patented by Hamilton of America in 1874. Some means besides the sickle and scythe, hoe and plow, were wanted to destroy obnoxious standing grass and weeds. A weed like the Russian thistle, for instance, will defy all usual means for its extermination. A fire chamber has been invented which, when drawn over the ground, will burn a swath as it advances, and it is provided with means, such as a wide flange on the end of the chamber, which extinguishes the fire and prevents it spreading beyond the path. A similar stove with jets of flame from vapor burners has been used to soften hard asphalt pavement when it is desired to take it up. The art of heating and cooking by oil, vapor and gas stoves is one that has arisen during the latter half of this century, and has become the subject of a vast number of inventions and extensive industries. Stoves of this character are as efficient and economical as coal stoves, and are in great demand, especially where coal and wood are scarce and high-priced. Oil stoves as first invented consisted of almost the ordinary lamp, without the glass shade set in the stove, and were similar to gas stoves. But these were objectionable on account of the fumes emitted. By later inventions the lamp has been greatly improved. The wick is arranged within tubular sliding cylinders, so as to be separated from the other parts of the stove when it is not lit, and better regulating devices adopted, whereby the oil is prevented from spreading from the wick onto the other parts of the stove which give rise to obnoxious fumes by evaporation and heating. Some recent inventors have dispensed with the wick altogether, and the oil is burned practically like vapor. Gasoline and other heavy oily vapors are in many stoves first vaporized by a preliminary heating in a chamber before the gas is ignited for use. These vapors are then conducted by separate jets to different points in the stove where the heat is to be applied. The danger and unpleasant flame and smoke arising from this vaporizing in the stove have been obviated by inventions which vaporize the fuel by other means, as by carbonating, or loading the air with the vapor in an elevated chamber, and conducting the saturated air to the burners, or by agitation, by means of a quick-acting, small, but powerful fan. Sterilizing. The recent scientific discoveries and investigations of injurious bacteria rendered it desirable to purify water by other means than filtering, especially for the treatment of disease-infected localities, and this gave rise to the invention of a system of heat sterilizing and filtering the water in one process and out of contact with the germ-laden air, thus destroying the bacteria and delivering the water in as pure and wholesome condition as possible. West in 1892 patented such a system. Electric heating and cooking. Reference has already been made in the chapter on electricity to the use of that agent in heating and cooking. The use of the electric current for these purposes has been found to be perfectly practical, and for heating cars especially, where electricity is the motive power, a portion of the current is economically employed. The art of heating and cooking naturally suggests the other end of the line of temperature refrigeration. A refrigeration by which ordinary ice is artificially produced, perishable food of all kinds preserved for long times, and transported for great distances, which has proved an immense advantage to mankind everywhere, and is still daily practiced to the gratification and comfort of millions of men, must receive at least a passing notice. The Messrs. E&F Carr of France invented successful machines about 1870 for making ice by the rapid absorption and evaporation of heat by the ammonia process. The discoveries and inventions of others in the artificial production of coal by means of volatile liquids, whether for the making of ice or other purposes, constituted a great step in the art of refrigeration. Vaporization, absorption, compression or reduction of atmospheric pressure are the principal methods of producing cold. By vaporization, water, ether, sulfuric acid, ammonia, etc., in assuming the vaporous form, change sensible heat to latent heat, and produce a degree of cold which freezes an adjacent body of water. The principle of making ice by evaporation and absorption may be illustrated by two examples of the Carr methods. It is well known what a great attraction sulfuric acid has for water. Water to be frozen is placed in a vessel connected by a pipe to a reservoir containing sulfuric acid. A vacuum is produced in this reservoir by the use of an air pump, while the acid is being constantly stirred. Lessening of the atmospheric pressure upon water causes its evaporation, and as the vapor is quietly absorbed by the sulfuric acid, the water is quickly congealed. It is known that ammonia can be condensed into liquid form by pressure or cold, and is absorbed by insoluble in water to an extraordinary degree. A generator containing a strong solution of ammonia is connected by a pipe to an empty receiver immersed in cold water. The ammonia generator is then heated, its vapor driven off and conducted to a jacket around the center of the receiver, and is there condensed by pressure of an air pump. The central cylindrical space in the receiver is now filled with water, and the operation is reversed. The generator is immersed in cold water and pressure on the liquid ammonia removed. The liquid ammonia now passes into the gaseous state, and is conducted to and reabsorbed by the water in the generator. But in this evaporation great cold is produced, and the water in the receiver is soon frozen. Twining's inventions in the United States in 1853 and 1862 of the compression machine, followed by Pictet of France, and a number of improvements elsewhere, have bid fair to displace the absorption method. In dispensing with absorption, these machines proceed on the now well-established theory that air and many other gases become heated when compressed, that this heat can then be drawn away, and that when the gas is allowed to re-expand it will absorb a large amount of heat from any solid or fluid with which it is brought in contact, and so freeze it. Accordingly, such machines are so constructed that by the operation of a piston, or pistons, in a cylinder, and actuated by steam or other motive power, the air or gas is compressed to the desired temperature, the heat let off, and the cold vapor conducted through pipes and around chambers, where water is placed and where it is frozen. By the best machines from 500 to 1,000 pounds of ice an hour are produced. The art of refrigeration and of modern transportation have brought the fruits of the tropics in great abundance to the doors of the dwellers of the North, and from the shores of the Pacific to the Atlantic and across the Atlantic to Europe. A train of refrigerator cars in California laden with delicious assorted fruits, and provided with fan blowers driven by the car axles to force the air through ice chambers, from whence it is distributed by perforated pipes through the fruit chambers, and wherein the temperature is maintained at about 40 degrees Fa, can be landed in New York 4 days after starting on its journey of 3,000 miles, with the fruits in perfect condition. But the public is still excited and wondering over the new king of refrigeration, liquid air. As has been stated, the compression of air to produce cold is a modern discovery applied to practical uses, and prominent among the inventors and discoverers in this line have been Prof. Dewar and Charles E. Tripler. Air may be compressed and heat generated in the process withdrawn until the temperature of the air is reduced to 312 degrees below zero, at which point the air is visible, and to a certain extent assumes a peculiar material form, in which form it can be confined in suitable vessels, and used as a refrigerant, and as a motor of great power when permitted to re-expand. It is said that it was not so long ago when Prof. Dewar produced the first ounce of liquid air at a cost of $3,000, but that now Mr. Tripler claims that he can produce it by his apparatus for 5 cents a gallon. Refrigeration is at present its most natural and obvious use, and it is claimed that 11 gallons of the material, when gradually expanded, has the refrigerating power of 1 ton of ice. Its use, of course, for all purposes for which coal can be used is thus assured. It is also to be used as a motor in the running of various kinds of engines. It is to be used as a great alleviator of human suffering in lowering and regulating the temperature of hospitals in hot weather, and in surgical operations as a substitute for anesthetics and cauterizing agents. It was one of the marvelous attractions at the Great Paris Exposition of 1900. Lighting is closely allied to the various subjects herein considered, but consideration of the various modes and kinds of lamps for lighting will be reserved for the chapter on furniture for houses, etc.